We're going to end this chapter with a discussion of power and how the independent and dependent t-tests compare on power. So just a quick reminder, power is the what we describe as the phenomenon of correctly rejecting HO. In other words, correctly detecting a treatment effect. And different statistical tests have more or less power than other tests. So if a test is powerful, what we mean by that is that it has a greater chance of correctly rejecting HO. If we compare the independent and dependent t-tests, all things considered equal, the dependent t-test is more powerful. And there are reasons for that. In order to understand the reason why the dependent t-test is more powerful, you have to remember what t does. All right, so when we calculate a t, that's the test statistic for a t-test, not only are we looking at the difference between the two means, the mean for group 1 and the mean for group 2, but we're also looking at how much error we have in our experiment. In other words, we are going to compare the difference between mean 1 and mean 2 relative to our error term. What's contributing to error in an experiment? Well, we have sampling error for one. We also have basically anything that is causing scores in of our dependent variable to fluctuate, and it has nothing to do with the independent variable. The only thing that should be making scores different is the independent variable. So anything else we can chalk up to error. Now, if you have different people in each group, then you can say another source of error we have is individual differences. If I have Peter, Paul, and Mary in group 1, well, Peter, Paul, and Mary have all these individual quirks, right? Personality quirks. And then if I have Tom, Dick, and Harry in group 2, I have a whole new set of people, a whole new set of quirks. So now we've got lots and lots of quirks that can be influencing the scores of the dependent variable, and it has nothing to do with the independent variable. And so we say that individual differences becomes a source of noise. Well, if you have a design where you test the same people in each group, so Peter, Paul, and Mary in group 1, Peter, Paul, and Mary in group 2, then you can run a dependent t-test, and that t-test allows you to statistically or mathematically remove the effect of individual differences in the calculation of your t-value. All right, so if you remove the individual differences, this is going to make the value of t larger. And I'll show you on the next slide, I'll show you how this is true mathematically. But just think about it just in terms of, your, logical deductions, right? So again, what we're doing with these t-tests is we're subtracting mean 1 from mean 2, okay? X bar 1 minus X bar 2. And then we're looking at the size of that difference, but that alone does not determine the size of your t. It's all relative to how much noise in your experiment. How big is your error term? So if we can make the error term smaller, then the difference between the two means becomes more obvious. Here's an analogy. Pretend you're in a very, very noisy room and somebody's trying to talk to you. Well, you might not hear what that person is saying because there's so much noise in the room, right? So even though you know there's a conversation going on, the person is speaking to you, you can't hear it. But if I were to suddenly tell everybody in the room, okay, whisper, don't, lower your voices, don't talk loud. Now the person beside me, even though they don't change their volume, now you can hear what they're saying. So this is a good analogy for what I'm trying to explain here. The difference between the means might only be detectable if you have a small error term. In other words, a little bit of noise. If you have a lot of noise, a big error term, then the difference between those two means might not be detected. All right? And I'll show you the mathematical explanation in a minute. Now, why do we care about this? Why do we care that, the t value becomes smaller with more noise, or the t value becomes larger with less noise? The reason why we care is because bigger t values bring us closer to the rejection zone. Do you remember that from chapter 7, where we said the bigger the test statistic, the closer it gets to the tails where those rejection zones are located? In other words, as the TS gets bigger, the frequency of the TS gets smaller, as does the probability. And if the TS is bigger than the critical value, then you're in a rejection zone. And once you reject HO, then you have a chance, at least, of correctly identifying a treatment effect. You cannot identify a treatment effect unless you reject HO, right? That's the first prerequisite, is you must reject HO, then you have a chance of falling into that 1 minus beta area where you would correctly reject HO. All right, so we want larger t values. T is just the test statistic for the t-test. We want these to be large. And so if dependent t-tests are more powerful, then that's really a good incentive for using them, right? Dependent t-tests, if it's the case that the people in group 1 are the same as the people in group 2, same set of people, in other words, your independent variable is within subjects. If the independent variable is within subjects and you use a dependent t-test, then you're going to have more power. And I explained why here about the error term getting smaller.